Hello, good morning. Can you hear
Good
me?
morning, sir. Yes, sir, you are audible, sir.
Good morning, very good morning to all of you. And welcome again to this second session of this workshop. And I hope all of you are doing well. And let me share my screen. See. See, one of my friend, Dr. Ige, is joining. He is from Nigeria. Dr. Ige, can you hear me?
Yes, I can hear you. Good morning.
Okay, good morning. Good morning.
Yes, thank you.
I just check if you can see my slides. Is it visible?
Yes, sir, we can see your screen.
Okay, good. Great. Then let us start today's agenda. And before going to today's part, just quickly look back whatever we have covered in the first lecture. Okay, so it was all about introduction of CFD. As this outline of this course suggests, the first lecture was all about introduction to CFD, what it is, why to learn, area of applications, prerequisites, etc. And we have also shown that what are the steps and some case studies. Okay, in some industrial problem and in some natural problem, how CFD can be employed. That thing we have discussed. Okay, so what is the definition? Then what are the different approaches to solve fluid dynamics problem? We have seen experimental routes are there, theoretical routes are there, and computational routes are there. And CFD belongs to this third category, that is this computational path of investigation. And this is the brief definition of computational fluid dynamics. What does it mean? And why we use CFD? Because it has a lot of advantage that we have discussed. Then benefits of CFD, it gives you the insight, foresight, and it can make the process efficiency. Process means makes the process more efficient. Okay, so it can enhance the efficiency. Then we took some examples in different sectors, starting from aerospace, automobile, biomedical, chemical processing, HVAC, hydraulics, marine, oil and gas, power generation, sports, pollutant monitoring, and also weather modeling. Okay, so weather ocean current prediction. Okay, so wind direction of wind, that everything can be calculated. So these are things. Then this is the governing equation that I just showed you. These are the different forces, and these are the different classifications of CFD problems. And then I told you that what are the basic requirements for CFD analysis. I told you that it is the clear understanding about the governing equation, especially Navier-Stokes equation, which is a set of nonlinear coupled PDEs. Then knowledge about the numerical method, especially how to solve initial value problem, boundary value problem. Then concept of discretization, concept of different types of boundary condition, concept of stability, consistency, a little bit of programming skill, and computer knowledge. Okay, so that is also important. Someone is waiting there. Yes. So these are the things. So in today's class, our emphasis will be in this point. We will try to understand this governing equation as much as possible. Then we will try to discuss a little bit of knowledge about numerical methods. After that, concept of discretization part, we will cover a little bit. We will try to complete the different type of boundary conditions, because these things are very vital thing. Okay, so unless and until you have a proper knowledge of it, you cannot formulate the problem. Okay, so this thing we will put emphasis today. So, and these are the different tools. After that, I told you different steps of CFD simulation. That is identification of geometry, then setting up the physics of the problem. That means fixing the governing equation. Then specification of the boundary condition, then specification of material properties, select the discretization methods, specify the solver and run the simulations, and analyze the results with post-processing. Then what is pre-processing? This is geometry development, this is meshing, this is defining the properties of fluids, then giving the boundary conditions, fixing the solver, and then post-processing. So today's lecture will be mostly focused a little bit of detail about this solver part. Okay, that how to solve, how to fix the governing equation, and then how to solve it. So this is the post-processing part, how you can visualize the results. So that things shown. Then we took some of the case studies. Okay, taking the industrial problem or biomedical problem, cardiovascular problem. This is a star tank problem. Then and the fluidized bed problem, fuel cell problem. This is some mixing tank problem, and this is boiling problem. And then I reminded you that do not rely if you are using some software, CFD software. Any question?
Technology.
Yes.
It's easy, but I haven't studied.
I think if someone is not talking, please mute it. If don't have any question.
It just contains flow sheets. Flow sheets.
Any question? Someone is asking, raising hand, I think. Okay. So then then this is just we have to be careful that whatever results we are getting from a CFD software, we cannot rely them blindly. Okay, so there are some steps. Okay, to check its validity. Okay, so that is called validation. Okay, so that thing we will discuss after the time. Now I told you to install student version of ANSYS Square and check in your computer if it is working. And I hope some of you have tested it. And we will discuss this part at the end of today's class. I will again come back to this point. But for the time being, let us come to the new session of today that will deal with the governing equations and the little bit of numerical methods. So this is now we will start this lecture 2, this part. Okay, so this part we will cover now. It is all about idea about governing equations and different discretization methods. So let us revisit this slide once more. We have seen it in earlier lectures also. And this shows mainly 3 equations. Okay, so first equation is known as continuity equation, which is basically conservation of mass. Okay, so conservation of mass we have studied from the very high school level. And however, if you try to mathematically formulate it, you will get an equation like this, continuity equation. Now you may ask that how these questions, this equation is coming. Okay, so there is an interesting story of derivation story. Okay, to see it because these equations are based on control volume approach. Okay, or let me not complicate it, but whatever physical laws we have studied in our school level are mostly based on Lagrangian approach based on control mass. Okay, so we are fixing a control mass and based on that we do our treatment. But in case of fluid mechanics, it is always useful to take a control volume approach. Control volume approach means you are just taking the control mass approach means you are this. Let's say this is a body. its mass is fixed. Now, if it moves from here to here, you are targeting that this mass is fixed, which is moving from one place to another, and you can do the necessary analysis. But in case of fluid, such fixing of mass is very difficult. This approach is not so good. So what we do, we take a control volume. Control volume means we fix a volume and we consider that some amount of flux of the flux, maybe mass flux, that means fluid flow, is entering in that volume and exiting from that other side, from other part. Okay. So whatever fluid are coming, that are passing through this control volume, and we are interested on this volume part, not the mass of this mass element of this fluid. Okay, so this is called control volume analysis. So whenever we are transforming the basic laws of physics from control mass to control volume approach, then we can get this kind of conservation equations. Okay, conservation equation based on this control volume. And if you do the analysis that whatever mass is entering and whatever is exiting, and if you change also consider the change with time, then you can arrive at an equation like this, which is known as continuity equation, where rho is your density and u is velocity and t is time, as you said. Okay, and this del dot rho u is an operator. This is vectorial representation. This is vectorial representation, and we use this vectorial representation because it is free of any coordinate. Now, this can be expanded based on the coordinate system. It can be Cartesian coordinate, it can be cylindrical coordinate, or it can be spherical coordinate. Any suitable coordinate can be taken. Now, conservation of mass principle will give you an equation which is known as continuity equation. Okay, so I am not just stopping here without going into detail of it. Any standard textbook of fluid mechanics will give you the detailed derivation of it. If you are interested, you can look into it. This is one of the first equation which is used in, which is considered as a basic equation of CFD. Now, second equation is the most important, I would say. So this is called Navier-Stokes equations. Okay, so now derivation of Navier-Stokes equation itself is a very interesting topic. Okay, and which is beyond the scope of this workshop, and it needs a number of class, and you can understand that how this equation is coming into picture. Basically, this equation is a representation of second laws of motion. Okay, so what we know that force equal to mass into acceleration, right? So that actually, when you convert it into a control volume domain or Lagrangian to the Eulerian transformation you do, then this kind of equation will appear. However, the derivation part I am not going. I am assuming that you know this, but for your interest, those who like to work on this domain, you must know that how this equation is coming. Okay, it coming into picture. So I'll just touch it. A couple of slides I will spend behind this equation. And again, this equation is in vector form. It can be, if you expand it in Cartesian coordinate, it is basically three set of equations like this. One in x direction, another one in a y direction, another one is z direction. And this third equation is all about your energy. If temperature change is involved, okay, so if temperature change is involved, then this particular equation will come, and this will come from conservation of energy. And by the way, this Navier-Stokes equation is basically momentum conservation equation. So if you conserve the momentum in a control volume, then you will get this equation. And if you conserve the temperature, you will get this third equation. These three equations are considered as the basic equations of CFD. However, in principle, temperature not reflected in the problems. Okay, if there is any problem which is isothermal in nature, where temperature change is not significant, then you can neglect it. Okay, so basically you have to solve this continuity equation and momentum equation for any case of fluid flow. Okay, so this solution of this continuity equation and Navier-Stokes equation is all about CFD. So, and since these are differential equation, you need to solve this in a particular domain. Okay, so where to solve it? Differential equation is applicable for a very small volume of element. So you need to solve this equation over a domain where you are interested. Let's say if you are interested to solve a pipe flow problem, you have a pipe like this where your water is entering from this direction and exiting from the other direction. Then you have to solve with both these equation in this particular domain, in this particular pipe domain. So you have to identify the geometry and then you need to select these two equations properly. Now, Navier-Stokes equation is an elaborate equation. It can be simplified based on the situation. Okay, so we'll see that, and then you need to solve it, right? So these two, I would say, let us now forget about this energy equation part. Okay, to simplify the situation. So this continuity equation and this momentum equation is basically the governing equation for CFD in most of the cases. I hope it is clear. Now, little bit discussion I will do about this continuity equation and Navier-Stokes equation because it is needed. So as I am again writing this continuity equation here, it states that del T of rho, that means this part is showing the temporal derivative. Temporal derivative means with respect to time, how mass is changing in a particular control volume. Okay, so that is indicated by this del rho del T. So this is temporal derivative, right? So it is called temporal derivative, and this particular term is associated to your means if anything is steady state. Let's say there is a pipe flow. Again, I am drawing a pipe, and the flow is entering and exiting, and it is in steady state. Steady state means with respect to time, there is no change in the flow pattern. Okay, so that means in that case, this part will be 0. So only this del dot rho u will exist. Okay, so this actually means del x of rho u plus del y of rho v plus del z of rho u. Sorry. So that is that you can, if you can expand in a particular Cartesian coordinate, it will look like this. Now, as I was telling you in the last class, CFD problems can be broadly classified into two parts. One is called incompressible, another one is called compressible. Okay, so let me remind you, CFD problems have two parts. One is called incompressible flow problem, and another one is called compressible flow problem. Now, compressible, incompressible meaning is very clear to you. If some material can be compressed, compressibility factor is there significant, then it has to be there. You have to consider that part. Now, mostly in aerial application, if you consider airflow or aerodynamic application, okay, or let's say weather forecasting, weather modeling, all these things, rocket movement, aeroplane movements, missile movement. So all these things will come under this compressible part. Okay. And incompressible flow means water flow, air flow, to a great extent, you can be considered as incompressible. Okay, so air almost, if it is below 100 meter per second, etc. Within this range, even air can be considered as incompressible. And in most of our industrial application for chemical, metallurgical, mechanical, even civil, etc., we will see that incompressible assumption is quite acceptable. In 90% cases, incompressible flow is there. So our discussion, whatever we are going to do, will be based on this incompressible part. However, the basic approach will be same for the compressible cases also, but the equation will have some extra term. So we will consider on the incompressible flow, and incompressible flow means you can consider density as constant. Okay, this rho will be constant. Now, if rho is constant, then you can take this rho out of this thing, this derivative term. So the continuity equation will stands like del dot u equal to 0. Okay, so this if you expand, then del u del x plus del v del y plus del w del z equal to 0, and in case of incompressible continuity equation. So this will be the form of this continuity equation. Okay, so this is basically mass conservation equation. So this can be considered as equation number 1 for your CFD problems. Now let us come let look little bit closer to the Navier-Stokes problem, Navier-Stokes equation. Any questions? Please, if you have any questions, you can ask me. Okay, stop me and ask me. Otherwise, mute your mic. So you see that here this part I also showed in the last class, and you see that this is showing the forces acting on a moving fluid element. Okay, so if there is any flow is taking place in a channel, and if you consider any particular volume element here, now what are the forces acting on this fluid flow, on this fluid element? So these can be classified broadly into two parts. Some of the forces that will be acting are called body forces, and some of the forces will be called as surface forces. Okay, so total forces acting on this fluid element in any fluid flow can be categorized into two parts. One is called body force, which depends on the mass of the body, and one is called surface force, which depends on the surface area of the body. Okay, so under the body force term, you have gravitational force or any other external force like electric force, magnetic force, electromagnetic force, etc. And surface force is basically two types: pressure force and viscous force. Now, viscous force again can be act from two directions. One is called viscous shear force, another one is normal force. Okay, so these are the different forces that is acting on this body, and if you apply Newton's second law on this body, then you can get the Navier-Stokes. So Newton's second law, what it states that means mass into acceleration will be equal to sum of the applied forces. So Newton's states that mass into acceleration will be equal to summation of all the forces acting on that body, right, on this particular body. If A is the mass, acceleration is denoted by A, then sum of the forces. Now sum of the forces means all these forces, this gravitational force, if there is an electromagnetic force, etc. Generally it do not remain present until and unless it's a very special situation, you are keeping any system in any electric field, etc. You did not consider that. But this pressure force and this viscous force will be present. Okay, now look into this right hand side of this Navier-Stokes equation that is written at the bottom. So this right hand side, this is the short vectorial representation of the incompressible flow Navier-Stokes equation. This rho is coming outside the derivative because it is incompressible assumptions is there. So let us first see the right hand side. What are there in the right hand side? There is one term called minus del P, which is actually pressure force due to pressure gradient per unit volume. Okay, so that means this is pressure force, this is being accounted here. And then there is this viscous force. So viscous force, viscous shear force per unit volume is indicated by this one. Okay, and your body force, this part is indicated by this particular term. So these three terms actually combines this summation of forces that we see, that is shown in the right hand side of it. And this left hand side is basically mass into acceleration. Now this mass and into acceleration can be shown by this rho into du dt. Means what? Du dt stands for acceleration, although it is actually not a normal derivative, which is called total derivative. So rho stands for mass per unit volume. All the terms are basically in unit volume terms. So their mass per unit volume is denoted by rho here. Now this is mass, and this capital D dt of u is denoting the acceleration term. Okay, so you see this is mass into acceleration equal to the summation of force, summation of forces acting on that particular volume element. So this Navier-Stokes equation is in a way representation of the second law of motion, Newton's second law of motion. Okay, but in a different form. Okay, in a control volume approach, if you pose the force equal to mass into acceleration, you will get this part. Okay, this is called Navier-Stokes equation. So the term you should know very clearly. Here, once more, the representation is shown a little bit elaborate manner. This is the general representations. Okay, so you see this total derivative that we have seen in the last slide. This part, this total derivative has two components. One is temporal derivative, and another one is convective component. Okay, so that is represented here. Del rho u del t. It is this rho is kept inside because this is general form applicable for incompressible and compressible both. And this term is actually convective term, which is associated with the bulk flow. Okay, so del dot rho u cross u, and then this is pressure force, this is viscous force, and this is body force. So sum of these forces, here it is mass into accelerations. Now can be simplified using del dot u equal to 0, because for incompressible flow we have seen that continuity equation can be represented by del dot u equal to 0. So that we have seen here, this part. Okay, del dot u equal to 0 for incompressible continuity equation. So that if you apply here, then this part, these convective terms can be simplified using this vector identity, and that will give you this thing u dot del u. Again, u dot del u can be replaced by this kind of I have not shown it. Okay, I'll come back to it. So this is the part, and this tau, which is denoting the viscous force in general, can be expressed in this form: mu into del u plus del u transpose minus 2/3 of mu into del dot u into identity matrix. So these are, this is actually our model, mathematical model for this viscous force. Okay, so what is its origin? If you like to know, you need to go back to your fluid mechanics or transport phenomena book. You can get the details that how this tau is coming. Now, if you simplify it, this is the model of tau. Now, if you take del dot tau, then it will come like this. And if you do little bit of simplifications, and if you consider del dot u equal to 0, it will give you mu del square u. Okay, so mu del square u, that actually we see here. This is, instead of mu, we divide the entire part with rho, both sides of this equation with rho, and this mu is kinematic viscosity, which is equal to mu by rho. That is shown here. Okay, so this is the incompressible flow continuity equation, del dot u equal to 0, and for incompressible flow you have del u del t plus u dot del u minus 1 by rho del p plus mu del u delta square u plus f equal to 0 plus f, which is basically the Navier-Stokes equation. And these two equations we need to solve in any particular domain, in any particular fluid geometry, and that is all about CFD. Now, once again, clearly let us see. So this is the thing, total derivative term, mass into acceleration per unit volume, that is shown in the left hand side. And if I expand this total derivative term, you know that total derivative means del t plus del dot some quantity. Okay, so here it is. If you expand it, you will get this part, del t of v. V stands for velocity vector, v dot del into v. So this total part is basically denoted by this total derivative. So mass into acceleration will be equal to external force, which is due to gravity, because in normal situations body force is present on Earth's surface as gravity, and then pressure force is there, and then some shear forces, means shear forces, internal stress forces, viscous effects, etc., that can be given by this. So this is all about your Navier-Stokes part. Now this up to this point we are writing this Navier-Stokes equation in the form of in the vectorial notation. This is vectorial notation. This is independent of any coordinate. Okay. Now if I like to expand this, but whenever we will try to solve any problem, it has to exist. It will exist in any coordinate system, right? It will be either in Cartesian coordinate system, or it can be present in a spherical coordinate system depending on the situation. Now, the selection of coordinate is very important. So, first thing, whenever you are setting up a problem to solve, you need to first identify the proper form of governing equation. That means you need to fix whether it is compressible or incompressible, or whether it is steady state or unsteady state. So by that way, you need to first fix the governing equations. Okay. Then second thing is important, that is called selection of coordinate. Okay, selection of suitable coordinate. Why it is important? Because based on that you need to choose that format. But before going into detail, let me show you the different formats that is applicable for the different forms of Navier-Stokes equation in different coordinates. So this slide is actually showing the Navier-Stokes equation in Cartesian coordinate. Okay, so Cartesian coordinate, you know that this is Can you hear me? Hello?
Yes, sir, you're audible now.
Yes, there was a power power cut in the department, and network is not coming. So I'm trying to join with my mobile data. So let us see if there is any discontinuity. Just get me notified.
Okay, sir.
Okay. So we are here. I think this slide was there, right? I was discussing this one when got disconnected. Navier-Stokes equation in Cartesian coordinate. Let me continue from here. I was just discussing this vector form and then in this vector form of Navier-Stokes equation can be expanded in different coordinate system. For example, it can be written in Navier-Stokes in Cartesian coordinates. What is Cartesian coordinate? You know that it has three axes: x, y, and then z. So in these three direction, if you write these three component of momentum equation, yes.
Screen is not visible, sir.
A slide not visible? Just a minute. Okay.
Yes, sir. Like this.
1 minute. Now.
Yes, sir.
Yes, sir. It's visible now.
Okay. So you see here, if this is the vector form of the Navier-Stokes equation. Now, if we expand it for Cartesian coordinate system for x, y, z direction, then x direction will be like this. So this is the left hand side where this rho stands for mass and this is for total derivative. It has two components. One is this temporal derivative del u del t, and another one is this convective component. Convective component is basically related to this AU, V, and W. These are actually bulk flow, means whatever flow field exists, that velocity is component. Now, do you see this part is making this equation a nonlinear? Okay, because you have velocity and again multiplied by del u del x, gradient of velocity. So this u multiplied by del u del x terms makes this entire equation a nonlinear one. Okay, linear equations are a little bit easy to solve, but due to this nonlinearity, it is very difficult to solve analytically, this Navier-Stokes equation. That makes this equation little complicated. Now, this is the left hand side, which stands for this mass into acceleration, which is represented by this one in x-axis, and this del p del x stands for pressure derivative. This is body force, gravity force, and this is the viscous force. Okay, so these three terms, this is for x direction, this is for y direction, and this is for z direction. And in Cartesian coordinate, these equations are written in incompressible form right now. Okay, so from now onwards, I will consider incompressible flow Navier-Stokes equation. If compressibility is there, little bit of different formation will be there, but the method will be remaining same. And this is the continuity equation. Now, why I am writing continuity equation again and again, and why these equations needs to be solved together, the reason is that if you look into each component of this Navier-Stokes equation, you will see that these three equations, x, y, z, momentum equation, are the three components of Navier-Stokes, and it constants unknown u, that means x directional velocity, v, and then w, means z directional velocity. So these three components are unknown, and along with these, you have this pressure. Okay, this pressure is also unknown. So you need u, v, w, and p. These four unknowns are there. So if you solve only Navier-Stokes equation in these three coordinate, you will get how much equation? Three equations. So there are three equations, but you have four unknowns. Okay, so there is no degrees of freedom are not matching. For solving four unknowns, you must have four equations, right? So we invoke these continuity equations here, which gives that additional equation. So if you consider this fourth equation where only u, v, w is there, so this entire set of equation becomes 4 and unknowns become 4. So this is now solvable. So that is why Navier-Stokes equations, momentum equations, and continuity equations are solved together. Because 4 equations, 4 unknown. This pressure term is additional there. We need an extra equation, and that comes in the form of continuity equation. Okay. Okay, fine. Now this is a Cartesian coordinate. Now, if I like to see continuity equation in different coordinate, then this is the part. This is in Cartesian coordinate. This is the form of the continuity equation. In cylindrical coordinate, this cylindrical coordinate means r, theta, z. Okay, so in that coordinate, this will be the format. in spherical coordinate, little bit of different form. Similarly, Navier-Stokes equations, if you see, this is what? This is equation in Cartesian coordinate. This is in Cartesian coordinate, and this is in cylindrical coordinate, r theta z format, and this is r theta phi. So selection of coordinate is very important from the problem's perspective. Now, how to choose whether you will solve the equations in Cartesian coordinate or spherical coordinate or cylindrical coordinate, that depends on the system geometry. If I ask you to solve a problem like this, that if you have a rectangular box like this and fluid is entering from one, your by default choice would be Cartesian coordinate, because Cartesian coordinate exactly map this system. But if I tell you to solve let us solve a flow through a vertical pipe. Okay, so that your liquid is coming from bottom and being ejected from the top. So if I like to solve, ask you to solve this problem, then should you apply Cartesian coordinate? You can apply, no problem with it, but it is better that if you choose cylindrical coordinate here. Okay, because cylindrical coordinate will give you an axis and one r direction and with a theta. So r theta z. So this is the z and this is r, and you have an angle here, theta, r theta z formula. So cylindrical coordinate will be helpful to describe this system. It will be always can you hear me? Hello?
Yes, sir.
No, yes, sir.
There is a phone call was there, that's why digits corrected. Okay. So if there is a system like spherical system, then it is always better to use the spherical coordinate system. So in CFD problem, first thing is that you set up the governing equation, that what would be the exact form of the equation that you are going to solve. Then second part is to select the particular coordinate, means what kind of coordinate will be suitable for your geometry. That is the second aspect. Okay. Now third thing, after setting, before going to that, this is also important that I like to show you that the equations that we are seeing here, these are differential form of the governing equation, means these are written in differential form. Okay. However, note that the same equations can be written in integral form also. Okay, so integral form means what? If you have to apply the Navier-Stokes equation or any differential equation in a particular finite domain, okay, then what you have to do? You have to integrate that equation in that particular volume element. Okay, in that case, this volume integral will come into picture, this surface integral will come into picture, and this surface integral will be there. Now, this volume integral to surface integral conversion is possible by the use of Gauss divergence theorem, etc. So I am not going into that, but remember, these are the representation of integral form of the Navier-Stokes equation. I am just showing an example, because this will be required whenever I apply finite volume method. The starting point will be this one rather than the differential form. Okay, so same Navier-Stokes equation which we generally see in the textbook in differential form, note that that can be also expressed in an integral form in this manner. Okay, so just remember this, the equation is same, the representation is different. One is differential form, another one is your this integral form. Okay, so this is all about the different forms of Navier-Stokes equation in different coordinate and meaning of each of the term. I will not go any more detail about this governing equation part. This much discussion will help you, will be helpful to understand CFD. Now we will go to the approach to solve this. So if you look into this Navier-Stokes equation, I am online, right? Yes or no?
Yes, sir.
Yes, sir.
Okay. Just respond me sometimes. Yes. Yes. Anything?
Sir, can you Then yes, sir. Can you please explain when we have to use the differential equation and when we have to use
System
the
integral
integral
equation.
form?
I will come into that. Everything will be clear. But you note that for the time being, you note that the same equation can be written in two forms, in differential form, which is very common, and integral form also is there. I will show you when finite volume method will be explained. Okay. Now, what you may ask, what is finite volume right now? If you do not know it, then that's why let me come step by step. It will be clear. Everything will be clear. So now let me start the solution approach for this equation. If you look closely, the Navier-Stokes equation, you will see that it is a set of coupled nonlinear partial differential equation. Please check it, means listen to me carefully. This is coupled, okay, then nonlinear, and then partial differential equation. These three components are there. Let me see that these equations, this whatever, let me consider this part, Cartesian part. You see that this u is x directional velocity, v is y directional velocity, and w is basically z directional velocity. Now these u, v, w are related. These are not independent, right? Because u velocity will be having some impact on v, on w, and vice versa. So all are coupled to each other. It is not a case that you just independently solve this thing. You have these equations are coupled. It needs to be simultaneously solved because actually they are dependent. The components are dependent to each other. That is why these are coupled equations. Okay, and nonlinearity is coming due to this part because your velocity is multiplied with this the gradient of the velocity. So this term makes this system nonlinear. Okay, then partial differential equation. You know that what.
Hello. Yes, sir. Are you there?
Am I audible?
Yes, sir.
Hello?
Yes, sir.
Actually,
Yes, sir.
now, so far internet was not there. Now power is also gone. So I am now working on my laptop. How much backup is there? I will continue. Okay. The slide is visible.
No, sir. Actually, it is not visible.
Not yet. Okay. Now,
Yes, sir. Now it
Yes,
is
sir, it's
visible.
visible.
visible?
Yes, sir.
Yes. Okay. Okay. Thank you. Just a minute. Okay. So, uh, so as I told you that Navier-Stokes equation is a set of coupled nonlinear PDEs. What is happening? Yes. It's fluctuating. Let me know if there is any discontinuity. So, my God. So, there is some problem. So you see here, this uh, there is some difficulty in this particular part. It is a set of coupled nonlinear partial differential equations, and it is difficult to solve analytically such problem because analytical solution is not for Navier-Stokes equation is a challenging problem, mathematical problem for last 100 years. If anyone can solve this Navier-Stokes equation analytically, he or she may get a Nobel sort of thing. Okay, so that is the kind of challenging task it is. Now the solution method that is available to us is taking the help of numerical approach. Okay, you the approach and
Your voice is cracking, sir.
Actually, your voice is cracking, sir. I think it is for your internet.
Hello. So your voice is cracking.
we
Sir, your voice is cracking. We cannot hear you.
change the net. Let me try once more. I have changed the network, means SIM card I have changed. If it works fine, otherwise we can reschedule it after some time. Because this is an important part I am going to discuss. You should know it. Now it is okay. Can you hear my voice?
Yes, sir. Now we can hear you.
Okay, let
Yes,
us try. But if it disturbs too much, let me know. Uh, okay, so what is the general strategy to solve a partial differential equation? That should be known to us, because our final objective is to solve Navier-Stokes equation, which is a partial differential equation. So how numerically we can solve a partial differential equation? That standard approach we should know. Okay, now what is that methodology or strategy to solve a partial differential equation? Is that you just convert the differential equations to a set of linear algebraic equations using suitable discretization scheme. Okay, so differential equation you cannot handle directly in a computer. You need to, from differential equation, you need to convert to a set of algebraic equations. And this method known as discretization method. Okay, so what is the first target? P in computer or in using numerical method? The differential equation and discretize it, and by doing that, the differential equation to a set of algebraic equations, and mostly linear algebraic equation. Okay, so the first step is to take the differential equation and we do discretization it. Discretize it to get a set of algebraic equations. That is the first thing. And these discretizations can be of different variety. One is known as finite volume method, then finite element method, and spectral method. And there are so many methods are available. Okay, and out of them, this finite difference method is very straightforward. Okay, very straightforward to understand and is widely used also. But for fluid mechanics applications, finite volume method has certain advantage. Okay, so most of the commercial software, means that ANSYS Fluent, etc., are written based on finite volume method. Again, there is some advantages of finite element method. That's why COMSOL multiphysics is written on finite element method, and lot of structural mechanics software, specifically for civil engineers application, those they rely on the finite element software. All these have different different to differential equation and to convert it to a set of algebraic equations. Okay, that is different. Ultimately, we will equation from a differential equation. Now, in this particular course, I will cover this finite difference method little bit. I will show you the approach. Okay, and if I start doing it on this kind of big equations, you will be clueless. Okay, you cannot digest anything. Okay, those who are the beginners. If you are expert already in CFD, then this is a different story. But if you are beginner here, if I like to discretize these big equations, then it will be complex. That is why most of the CFD textbook or CFD course, you will see that they start with a very simple equation, simple heat transfer equation they start, or any general transport equation or advex equation they start with limited number of terms. And if you can understand the philosophy with that simple equation, that thing can be adopted for this kind of big equations also. Okay, that is possible. Now that is why we will also follow the same method. We will take a simple equation first, simple partial differential equation first, maybe a heat transfer equation, and we will try to solve it following finite difference or finite volume method. For example, one-dimensional unsteady heat conduction problem, which is a simple second order differential equation. So that if we can solve that problem, that methodology can be adopted to these kind of big equation also. That we will see later. But let us first understand with the help of a single equation that we will cover. Okay, so the first step that that we have to take is to convert the differential equation to a set of algebraic equation by the help of a suitable discretization scheme, which is known as FDM, FVM, or FEM, etc. Now, after getting the set of algebraic equation, you need to solve them. Now, there are a number of methods available in numerical text for solving a set of linear algebraic equations. Most simple or probably the widely used is the Gauss elimination method. Okay, that you have probably learnt in any of your mathematical courses or numerical courses. Now, Gauss element method, or in CFD application, we more prefer to TDMA method or Thomas algorithm, tridiagonal matrix algorithm or Thomas algorithm. Okay, so TDMA method or Thomas algorithm is more preferred in a CFD application, and also another method which is known as Gauss-Seidel method. Okay, so these methods are very popular in CFD solver as a CFD solver. So these are numerical methods for solving a set of algebraic equations. And since after discretization we are getting a set of algebraic equation, we need to either adopt Gauss elimination method or TDMA method or Gauss-Seidel method, etc. Then after discretization and after getting the proper algebraic equation solution method, and those who do not know what is Gauss elimination, TDMA or Gauss-Seidel, please go back to the numerical text and revisit it once. Okay, that will be clear. Things will be clear to you. Then third thing is important is to apply proper boundary conditions. Okay, because this differential equation, when you are going to solve, these will be either initial value problem or boundary value problem. Okay, so in case of boundary value problem means your values at the boundary will be specified. Okay, and if it is an unsteady problem, also initial condition will also be provided. Okay, that at initial time t equal to 0, you're at x equal to 0, the value is this. Okay, so that is also possible. So identification of boundary condition is important. Now, boundary conditions may be of different variety. It can be Dirichlet boundary condition. It can be Neumann-Tauip boundary condition. So now what is Dirichlet? What is Neumann? We'll discuss a little bit. That should be known to you. That's why in the prerequisite part, I told you that little bit of numerical knowledge is needed to understand CFD. I briefly touch these things so that you understand this course. I am online. My voice is audible, right?
Yes, sir.
Yes, sir.
Please confirm. Okay. Okay. Then the fourth part that is also important for as a numerical procedure is to understand something about the numerical errors. Okay, so numerical errors are basically of it's called round of error, and the moment you are converting a differential equation which is based on continuous function and you are discretizing it, that means you are trying to solve it in discrete points rather than it is a continuous function. You are basically incorporating some error in it. Okay, so that is called comes in the form of truncation error. And round of error is that if our computer has limited capability to handle after the digital pace, means let's say up point you can take maximum 8 to 10 digits or 20 digits, but it has some limit. Okay, so after that you have to truncate it. So that is called round off. You have to round off it. So that is called round off error. Okay, so this error, although you may think that after point there are so many digits, so that is very insignificant. But when you are running a simulation for thousands of steps or lakhs of steps, then that will actually accumulate to a good amount of error. Okay, so which you cannot neglect. So how to optimize this error part, that is also an important factor. For technique of for understanding how Navier-Stokes can be solved. Now, Navier-Stokes is a partial. You need to know how partial differential equation in a moment. Then you need to know how to choose
So
the
your voice
linear,
is tracking.
how to apply. Yes, now I am helpless. I don't have any other option to do. If it is too much cracking, then I can stop it here. Start again at 3 p.m. Okay, because any at 3 p.m. today, because I have to make up the last Sunday's class. So if you want, I can continue. Otherwise, I'll go home and sit after lunch. Okay, so 3 p.m. is a good time. I think all of you also we can in our department nothing is there. So what do you suggest? Should I continue for some or we should stop? What the organization is saying?
So we can continue from 3 because that will be easy for us to understand.
That
We have internet issues there.
okay,
We can
then we can.
continue from 3.
Yes, like this. Then let us stop here. This is an important part, but all of you, those who have interest in, please be present in 3 because
Yes, sir.
this is going to be an important topic today. Okay,
Yes, sir.
so let us meet again at 3 p.m. Okay, we'll just.
Okay.
Okay, thank you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.